Welcome to Chapter 5, the final chapter of the Introduction to Nanomaterials series. We've covered what nanomaterials are, how to make them, how to characterize them, and what unique properties they possess. Now we'll see how these remarkable properties are being applied to solve real-world problems in electronics, medicine, and energy. We'll also explore how artificial intelligence is accelerating nanomaterial discovery and discuss the important topics of safety, sustainability, and regulations. By the end, you'll appreciate both the tremendous potential and the responsibilities that come with nanotechnology. Quantum dot displays, marketed as QLED, represent the most commercially successful application of nanomaterials in consumer electronics. The concept is elegant. A blue LED backlight provides the base illumination. Quantum dot films convert some of this blue light to precise red and green wavelengths, and color filters complete the system. Because quantum dots have narrow emission peaks, QLED displays achieve color gamuts at or above 100% of the DCI P3 standard used in cinema, far better than the roughly 72% of the NTSC gamut typical of conventional LCD backlights. Peak brightness on high-end panels reaches several thousand nits, crucial for high dynamic range content. Unlike OLED displays that can suffer burn-in from static images, QLED panels are far less prone to it because they are LCD-based, lit by a uniform backlight rather than by per-pixel emitters. Samsung, Sony, and other manufacturers have brought QLED TVs to market, and the technology continues to improve with electroluminescent QLED displays that emit light directly from quantum dots. Carbon nanotubes and graphene offer pathways beyond silicon's fundamental limits. Laboratory transistors using carbon nanotube gates have been demonstrated at gate lengths near 1 nanometer, well below the physical gate lengths in production silicon, whose node names such as 3 nanometer no longer refer to any physical dimension. Their electron mobility exceeds silicon, and they generate less heat. Major semiconductor companies are actively researching CNT-based logic for future nodes. Graphene's extraordinary properties, including electron mobility of 200,000 square centimeters per volt second and thermal conductivity of 5,000 watts per meter Kelvin, make it attractive for many applications. High-frequency transistors exploit graphene's mobility for RF electronics. Transparent conductors using graphene or CNT networks can replace indium tin oxide in touchscreens, offering flexibility that brittle oxides can't provide. Thermal management solutions use graphene's conductivity to dissipate heat in electronics. While challenges remain in large-scale manufacturing and consistent properties, carbon nanomaterials are steadily moving from lab curiosities to commercial products. Nanoparticle-based drug delivery addresses fundamental challenges in medicine: how to get drugs to the right place at the right concentration with minimal side effects. Several nanocarrier types are now clinically approved. Liposomes are lipid bilayer vesicles that can encapsulate both water-soluble drugs in their interior and lipid-soluble drugs in their membrane. Doxil, a liposomal formulation of the cancer drug doxorubicin, reduces cardiotoxicity compared to free drug. Albumin-bound nanoparticles, such as Abraxane, reformulate paclitaxel without toxic solvents, improving delivery. Most remarkably, lipid nanoparticles enabled the rapid development of mRNA vaccines for COVID-19. These particles protect the fragile mRNA from degradation and facilitate its entry into cells. Tumors preferentially accumulate nanoparticles through the enhanced permeability and retention effect because their leaky blood vessels allow particles to extravasate while poor lymphatic drainage retains them. Active targeting adds antibodies or ligands to particle surfaces for cell-specific delivery. Controlling how drugs release from nanocarriers is crucial for therapeutic efficacy. Different release profiles suit different applications. Burst release delivers drug rapidly, appropriate for acute conditions. Sustained release maintains constant drug levels, ideal for chronic therapies requiring steady-state concentrations. Triggered release holds drug until a specific stimulus, like low pH in tumors or elevated temperature from hyperthermia, activates release at the target site. The Korsmeyer-Pepys model describes release kinetics mathematically. The release exponent n indicates the mechanism. N equals 0.43 for Fickian diffusion through spherical particles. Values between 0.43 and 0.85 indicate anomalous transport combining diffusion and erosion, and n equals 0.85 approaches zero-order release. Designing nanocarriers for specific release profiles requires understanding these mechanisms. Particle size, matrix composition, surface chemistry, and environmental responsiveness all contribute. The goal is matching release kinetics to the pharmacological needs of the drug and disease. Nanomaterials enhance medical imaging across multiple modalities. Superparamagnetic iron oxide nanoparticles serve as T2 contrast agents in MRI, darkening tissues where they accumulate. Their biodegradability and iron-based composition offer safety advantages. Gold nanoparticles provide X-ray contrast in CT imaging because gold strongly attenuates X-rays, and they can be functionalized for targeted accumulation in tumors. Quantum dots enable multiplexed fluorescence imaging because different sizes emit different colors. In research settings, quantum dots can simultaneously label multiple biomarkers in tissue sections or track cells in vivo. Photoacoustic imaging combines optical contrast with ultrasound resolution. Light-absorbing nanoparticles like gold nanorods or carbon nanotubes convert laser pulses to acoustic waves detected by ultrasound transducers, enabling deep tissue imaging with high contrast. Multimodal nanoparticles combining capabilities, such as fluorescence for surgical guidance and MRI for preoperative planning, are active research areas. Batteries are being transformed by nanomaterials. Silicon can store 10 times more lithium than graphite per unit weight, but bulk silicon cracks during charging as it expands by 300%. Silicon nanoparticles accommodate this expansion better, enabling practical high-capacity anodes. Nanostructured cathode materials like lithium iron phosphate benefit from shorter lithium diffusion paths, enabling faster charging. Graphene additives improve electrical conductivity throughout electrodes. Carbon nanotube networks provide mechanical stability during cycling. Beyond incremental improvements, nanomaterials enable new battery chemistries. Lithium-sulfur batteries could offer much higher energy density than lithium-ion, but sulfur is insulating and intermediate polysulfides dissolve into the electrolyte. Nanostructured sulfur cathodes and carbon hosts address both problems. Solid-state batteries replacing liquid electrolytes with solid ion conductors promise safety improvements, and nanostructured interfaces are key to achieving sufficient ion transport. Nanomaterials are opening new frontiers in solar energy conversion. Quantum dot solar cells exploit unique physics unavailable in bulk semiconductors. Multiple exciton generation, where one high-energy photon creates multiple electron hole pairs, can theoretically exceed the Shockley-Queisser efficiency limit for single junction cells. While this hasn't yet been realized in practical devices, research continues. Quantum dots' tunable bandgaps also enable tandem cells optimized across the solar spectrum. Perovskite materials, with ABX3 crystal structure, have emerged remarkably quickly. Starting from 3.8% efficiency in 2009, perovskite solar cells now exceed 25%, rivaling silicon. Their nanocrystalline nature contributes to defect tolerance and solution processability. Low-temperature synthesis enables low-cost manufacturing. Plasmonic enhancement using metal nanoparticles increases light absorption in thin absorber layers through near-field enhancement and light scattering. This allows using less material while maintaining efficiency. Clean energy technologies depend critically on electrocatalysts. Fuel cells need efficient oxygen reduction at the cathode, Water electrolyzers for hydrogen production need efficient hydrogen evolution. Both reactions benefit enormously from nanoscale catalysts. Platinum remains the benchmark for both reactions, but its scarcity and cost drive research into alternatives and optimization. Nanostructured platinum shows dramatically higher mass activity than bulk. Alloying with transition metals like nickel or cobalt creates surface platinum with modified electronic structure, further improving activity. Platinum skin structures with platinum-enriched surfaces over alloy cores combine stability with activity. The improvement is striking. Mass activity can increase by an order of magnitude going from bulk platinum to optimized nanostructured catalysts. Beyond precious metals, research explores earth-abundant alternatives. Nickel, cobalt, and iron-based catalysts show promise for hydrogen evolution. Nitrogen-doped carbon materials are emerging for oxygen reduction. Nanotechnology enables these developments through controlled synthesis and characterization. Artificial intelligence is transforming how we discover and optimize nanomaterials. Traditional materials development is slow and expensive, often requiring years of trial-and-error experimentation. Machine learning accelerates this process by learning patterns from existing data. Property prediction models take as input features like composition, size, and synthesis parameters, and output properties like bandgap, catalytic activity, or toxicity. Random forests, neural networks, and other algorithms can achieve high accuracy on problems where enough training data exists. Synthesis optimization uses ML to find optimal reaction conditions, reducing the number of experiments needed. Inverse design goes further. Given target properties, the model suggests compositions or structures likely to achieve them. Data comes from literature mining using natural language processing to extract quantitative results from publications, high-throughput experimental platforms that rapidly generate systematic datasets, and computational databases like Materials Project. As these datasets grow and models improve, AI-guided experimentation is becoming standard practice in materials research. Responsible nanotechnology development requires understanding and managing potential risks. Nanotoxicology studies how nanomaterials interact with biological systems. Size matters. Nanoparticles can penetrate biological barriers that block larger particles, including cell membranes, the blood-brain barrier, and the placenta. Surface chemistry determines how particles interact with proteins and cells. Reactive surfaces may generate reactive oxygen species that cause oxidative stress. Dissolution releases ions, which is why cadmium-containing quantum dots raise concerns despite their utility. The same properties that make nanomaterials useful, high surface area and reactivity, may contribute to toxicity. Exposure can occur through inhalation in occupational settings, ingestion from food packaging or consumer products, dermal contact, or intentional injection in medical applications. Safety assessment requires systematic testing. In vitro cell studies screen for acute toxicity, followed by in vivo studies for biodistribution and chronic effects. Understanding mechanisms enables designing safer materials from the start. Sustainable nanotechnology balances innovation with environmental responsibility. The 12 principles of green chemistry apply directly. Use non-toxic precursors, minimize waste, design for energy efficiency, use renewable feedstocks, and consider the full life cycle. Life cycle assessment examines environmental impact from raw material extraction through synthesis, use, and disposal or recycling. For some nanomaterials, the energy cost of synthesis is substantial. For others, the benefits during use, like improved catalyst efficiency, more than offset production impacts. End-of-life management is crucial, particularly for nanomaterials containing toxic elements. Regulatory frameworks are evolving to address nanomaterial-specific concerns. The European Union requires registration under REACH for nanomaterials produced above 1 ton per year, with specific provisions for nanoforms. The US EPA uses significant new use rules under TSCA to evaluate new nanomaterials. Japan has voluntary guidelines. Safe by design approaches incorporate safety considerations from the earliest development stages rather than treating them as afterthoughts. The future of nanomaterials is extraordinarily promising. In quantum technologies, nanomaterials serve as qubits for quantum computing, offer ultrasensitive quantum sensors, and enable quantum communication networks. Single photon emitters from quantum dots and color centers are key components. For sustainable energy, next-generation batteries using solid-state architectures or lithium-air chemistries depend on nanomaterial development. Electrocatalysts for green hydrogen production and CO2 conversion to fuels are active research areas with enormous potential impact. Personalized medicine will leverage nanoparticles for the ranostics, combining therapy and diagnostics in single platforms. Gene delivery using lipid nanoparticles, proven by mRNA vaccines, opens doors to gene therapy and gene editing. Organ-on-chip platforms using nanofabricated structures enable personalized drug testing. Perhaps most transformative is the integration of AI throughout nanotechnology. Autonomous laboratories can synthesize and characterize materials with minimal human intervention. Inverse design algorithms propose novel compositions. Self-optimizing synthesis adjusts conditions in real time. We're entering an era of accelerated discovery. Let's reflect on our journey through this series. In Chapter 1, we learned that nanomaterials are defined by having at least one dimension between 1 and 100 nanometers, and we classified them as 0D, 1D, 2D, and 3D structures. Quantum confinement and surface effects give nanomaterials their unique properties. In Chapter 2, we explored synthesis strategies from top-down methods like ball milling and lithography to bottom-up approaches including CVD, ALD, sol gel, and hot injection. The Lamur model explained how to achieve monodisperse particles. In Chapter 3, we mastered characterization techniques: TEM for direct imaging, AFM for surface topography, DLS for solution sizing, XRD for crystal structure, XBS for surface chemistry, and BET for surface area. In Chapter 4, we understood size-dependent properties: LSBR in metal nanoparticles, quantum-confined emission in quantum dots, superparamagnetism in magnetic nanoparticles, and enhanced catalytic activity from high surface area. Now in Chapter 5, we've seen these properties applied in electronics, medicine, and energy, and we've considered how AI is accelerating discovery while maintaining safety and sustainability. As we conclude this series, here are the key messages to take away. In electronics, quantum dot displays are already in our homes, and carbon nanotube and graphene electronics promise to extend Moore's law beyond silicon's limits. In medicine, nanocarriers are transforming drug delivery, from approved cancer therapies to the mRNA vaccines deployed against COVID-19. Diagnostic imaging benefits from contrast agents with targeted accumulation and multimodal capabilities. In energy, nanomaterials enable higher capacity batteries, more efficient solar cells, and better catalysts for clean hydrogen production. Artificial intelligence is revolutionizing how we discover and optimize nanomaterials, turning months of experimentation into days of computation-guided synthesis. And through it all, we must remain mindful of safety and sustainability, understanding nanomaterial toxicology and designing responsibly from the start. Nanomaterials are transforming technology across every sector, and this is truly just the beginning. Thank you for joining me on this journey through the world of nanomaterials. I hope this series has provided a solid foundation for your continued exploration of this fascinating field.